it kind of breaks your overdependence on the integral function, definite integral function on the calculator, because it's based on some general function f of x rather than a particular function. If it's a particular function, like antiderivative of x squared over an interval, then by all means plug it into your calculator, get an answer. But when it's given a general function, you can't make an assumption of what type of function that is. It could be trig, it could be exponential, it could be anything. So you can't just make it up as you go along. You have to kind of limit yourselves to the properties. I did hit record, right? Okay, good. Right, so let's take a look at these babies. So 0 to 6 is the interval that we're working on, or that we want to find. And what we talked about last time is that an antiderivative over an interval is an accumulation of area on that interval. Right? And so what we're looking at here is an x value that starts at 0 and ends at 6. One of our properties tells us that we can actually break up an interval into its component pieces. Fortunately, if you look at the intervals that are given to us, it says from 0 to 3 and then from 3 to 6. Well, if you put those two together, you're going from 0 to 6. No. All right. Now, graphically, I mean, you don't really need anything too elaborate, but basically what that's saying is, I'll just kind of chuck it over here. And maybe I'll offset it a little bit, so I'm only focusing on positive stuff. That's fine. So you have some kind of graph here, right? Starts at 0, ends at 6. Within that bounded area, you have, or that bounded region, you have a quantifiable area, right? Some numeric value that represents that area. What A is telling us to do is break it up so that instead of going from 0 to 6 directly, you go from 0 to 3, get that area, and that ends up being 4. They gave that to us. And then go the rest of the way. Go from 3 to 6, we have that area as -1. Now, my diagram is not consistent with that area because negative areas occur below the x-axis, but it's enough to give you a general sense of what's going on. All right, so what that's telling me is that if I take the 4 and add to it the -1, I will get the net area on that interval, which would be 3. Right? And that points to one of the properties, but I don't know. Let me see if there's a way I can say this in a reasonable way. If you understand the underlying concept, you don't need to memorize properties. So visually, this is saying that these two parts make up the whole. So why do I need to memorize a property in order to understand that? Right? B is a little different. But C is along the same lines as what I'm talking about, where if you kind of think about what those boundaries of integration are telling you, then you already have the answer without even really thinking about it. All right? Now, looking at B, you see you have a 6 and a 3. One of the givens has a 6 and a 3. The problem is it's in the reverse order. So what I can do is negate my integral and switch the boundaries of integration. That's one of the properties on the previous page. And if I do that, I'm looking at a negative, and then 3 to 6 for the f of x gives me a -1, and so we end up with a 1 as a result. So let me come up with a visual for that one. Aside from this crappy pen. I meant to put in a work order to get this fixed, but I didn't, so here I am again. All right, so you have an interval from 3 to 6, so let me come up with another sketch, something relatively representative. Classic arbitrary graph in calculus, they always look the same. Okay, what again we're looking for is the area bounded between these two functions, between these two verticals underneath the function. All right. What you're going to have when you're looking for area is a height at any particular point based on your f of x. But you're also going to have some base length. All right. So what's happening under normal circumstances is that you would be going from 3 to 6. That would be a movement in the positive direction. All right. So if I wanted to find that distance, I would just do 6 minus 3. It's a movement of 3 units. But if I were going the other way, if I were going from 6 to 3, that would be in the negative direction. Off the grid again. Negative direction. To get that distance, you would do 3 minus 6, which is negative 3. All right, so depending on the direction of movement in your accumulation of area, you could be looking at a positive or a negative base. So basically all this is telling us is to get from one to the other, it's only a negative factor that distinguishes them. So if you know going one way will give you a positive area, then going the other way will give you a negative area. In both cases, the height would be the same quality of number, either both positive or both negative. That's not necessarily relevant. Right? But if I'm looking at area of a rectangle at base times height, and I know the height is going to be positive, then the only thing that's going to impact the sign of the area would be the length of the base, whether it's positive or negative. Going from left to right, you have a positive base. Going from right to left, you have a negative base. So that's where that rule comes from that allows you to swap boundaries of integration. But as long as you negate the integral, you're in good shape. Right? Not always. Not always. It's always the same quality of number, depending on if you're going from the left to the right. So it could be positive or negative. All right. Part C. Call that the good old common sense rule. It's only common sense if you have an understanding of what a definite integral is. All right. It's not common sense to anybody looking at it. I mean, if you just walked into calculus for the first time, never took any calculus class before, and you saw that problem, that's not common sense. But if you understood where these things are coming from, then that one should be pretty straightforward because, again, we're accumulating areas. So what this is saying is I'm starting at 3. I'm ending at 3. So I have a curve. I'm starting at 3 and I'm ending at 3. I've accumulated no area. There's no width. So there's no width, so how could there be an area? All right, you have a height, but area is base times height. If I'm telling you that the base is equal to 0, 0 times the height is 0, so you're going to get a result of 0. If you always have it in your mind that you're looking for areas when you're finding a definite integral, it tends to answer a lot of your questions. Okay. Then you have part D, which is a nice one also. You have a constant multiple. Constant multiple rule is your best friend in calculus. Works for everything. Limits, derivatives, antiderivatives, summations. It's just telling us if we have a constant, we can just pull it right out of the whole shebang. And since this baby right here was a given piece of information, try to fix that 3 anyway. Whoa, that just made it worse. I'm going to release. Okay. Q, check. So negative 5 times negative 1 is going to give us a negative, positive 5. Yawn.
Ryan, why is the constant in front of the function? Because if it's just the area from 3 to 6, is it saying 5 times that area?
Yep. So it's basically saying that if you have a function, or if you're taking the integral of 5, forget about the negative, 5 times the function itself, you're going to build a function here, right? Now, it increases height by a factor of 5, so it's all the way up here. It's going to account for 5 times the area. So that doesn't end up being any different than it would be if you were to find the area up under the function itself and then multiply that equal 5. I'm just thinking about the analog for derivatives. So if you took the derivative of, let's say, 5 times x, that would be 5 times the derivative of x, which is 5 times 1. Yeah, so it works out the same way. Whatever the slope would be of the parent function, in that case x, you would multiply by whatever the coefficient is. So it's a scaling factor, really, more than anything. That's kind of cool in that regard. I think the trickiest type of question is the second example here. Because, well, it's the trickiest because it's a trick question. So that's your rationale right there. So 0 to 2, you look at it and say, do I have enough information? I don't know. But there, believe it or not, is plenty of information, a sufficient amount of information. It says, given the shaded region A has an area of 1.5. All right? So what they're giving us is a total area. All right? That's an absolute measure. All right, so they're saying physically, forget about negatives, forget about positives. Physically, there is a printed area. That printed area has a value associated with it. So ignoring direction, if I were to put infinitely many rectangles in here, measure the length of each rectangle and the width and multiply, I would get some numerical area. Because it's below the x-axis, that net area equivalent would be negative. All right, so the net area associated with this would be equal to negative 1.5. That's a poor quality negative. So negative 1.5. That's a poor quality decimal point. So 5 is also poor quality, but I'll live with it. All right. So the net area is negative 1.5. So what's the big deal? You say, okay, cool, fun fact of the day. Why do we care about this? Well, the net area is what you get when you find a definite integral. That's the kind of integral, or that's the kind of calculation that gives you positive and negative areas, and or negative areas. So this is the integral on 0 to 2 of my function f of x dx. All right, that value would be negative 1.5, right? So that's this guy right here. So I'll just draw a little arrow. All right, so that actually happens to be the answer to part A also, so that's good news, negative 1.5. total area always has to be positive. So if you have a component of a graph that's above the x-axis, that's going to be positive anyway, then your net area and your total area for that part would be the same. It doesn't matter. It's when it's below the x-axis, to make a net into a total, you just drop the negative sign. So, now we get to part B, and it's all this stuff. We got a couple of different properties. I don't want to say a lot, but a couple of different properties going on here. One of which is just simple addition. All right, don't let the brackets mess around with you. This is saying on 0 to 6, we have the function 2 added to, also in the interval of 0 to 6, the function f of x dx. Part of which we already have as an answer, because it was given. Right? Yeah. And of course the tail, just because. So I know that part is 3.5. And that's the sum and difference rule for integration. It tells us that we could break up an integral by a plus or a minus sign. It works differently for multiplication and division, as you know from derivatives. You can't just break up a product into two different integrals, but you can with a sum or a difference. So that's always a good step one. A good step 1A would be to look for something like a constant multiple and pull that, right? Now, this other part, you can go about it any way you want, this guy right here. It's numerical, so you can put it in the calculator, but again, the key, I think, anyway, through all my years of experience, the key to actually becoming good, not just getting stuff right, but getting good at integration, and also kind of knowing what the hell you're doing, is to get a good visual understanding of what an integral is telling us. So let's actually take a minute and see what this one is telling us. On the interval of 0 to 6, so I'll draw that diagram. So I'll come up with my interval of 0 to 6. We have the function f of x equals 2. So 2, just the 2, constant 2. Well, whatever you put within an integral, that's a function, right? That's a y equals. So it's saying y equals 2, which is a horizontal line. And I'll just chuck in a y equals 2, right? That's an attempt at drawing a horizontal line. It didn't really play out, but we'll live with it. All right, so I'm looking for the area bounded between that line and the x-axis on the interval of 0 to 6. I don't have to put infinitely many rectangles in there in order to figure this out. This has a base of 6 and a height of 2. So it has an area of what?
12.
Area of 12. So I know what my integral is. The antiderivative of 2 on the interval of 0 to 6 is 12, which gives us a final answer of 15.5. Now, if you like shortcuts, 15.3. Like I can't walk and chew gum at the same time. So 15.5. If you want a shortcut, the best shortcut is the calculator, right? Because that's like the ultimate shortcut. But if you'd like a shorthand way of doing it that doesn't involve a calculator, what did we really do? We found the distance along the x-axis, right? Which turned out to be the difference between the boundaries of integration. And then we just multiplied it by the height of the function. Since the height of the function was constant at 2, really all we ended up doing was taking 2 and multiplying it by the difference between the boundaries of integration. So if this was going from 3 to 6, you had a 2, then it would be 3 to 6, which is 6 minus 3 is 3, times 2 gives you a result of 6. All right, so people have said in the past that they like doing it that way. I think gives you a pretty solid understanding. I was looking for another example. I don't think I have one on here. It's really up to you because, yeah, you could get stuff right on a test just by popping it into your calculator, but there is a reckoning. You know, what happens is in the level of math that you get to that relies on you already understanding, knowing, understanding, and being able to do this kind of stuff, you're going to fall flat, right? Because you're not going to have that intuitive understanding, right? And that may be in this course, it may be in the next course. You might say, well, I'm not taking a math after Calc 2, so awesome stuff. The problem is, it may be like Unit 3 in this course that you need to have an intuitive understanding of this concept. And if you don't, that's going to be a problem.
Using like, why would you take the entire derivative to
You could, using the fundamental theorem, that would give you 2x. Then you plug in the 6.
and subtract
And you get the same thing. All right. The only reason I would even consider doing it this way, the graphical way, is because I have a constant function. If I had a constant function or something based on a property where I knew parts of it would cancel out, then I tend to go by hand, or at least using a graphical approach. That would be a case where you have, let's say, an odd function that is symmetric in terms of the boundaries of integration. So just a rough sketch real quick. If you had, probably stealing my own thunder a little bit. Ugh. Oof. Oh boy, that was so painful. So let's say this is negative a, and this is a. All right, not a to b because I want to guarantee that the boundaries are symmetric. If I, and I'll call it f of x because I'm very creative. If I were integrating from negative a to a, this function f of x dx, where x is an odd function, oh my god, this is out of hand. The result is going to be 0. All right, the reason why it would be 0 is because these two areas would be the same in absolute value. One's negative, one's positive. Added together, they're going to cancel each other out to 0. Right? But in the sense of net area, you get 0, but in the sense of total area, and for this one, you would drop the negative and then add it to this one. You would end up with whatever this is, double. So then you think of it that way and you say, okay, if I have a good intuitive understanding of the graph, then I could find the interval going from 0 to a, get that answer, because anytime you incorporate 0 into your calculations, it makes it a lot easier, right? So I go from 0 to a, and then just double that answer. Right? So it's kind of like graphical manipulation to meet your own needs. And instead of kind of like that, it's exactly that. All right, but anyway, so that'll be visible again if you want to see it. Part C, the integral going from 0 to 6 of the absolute value of f of x dx. All right, so that's saying that if there are negative components to this graph, you have to drop the negatives. So we're looking at this boiling down to the integral going from 0 to 2 of f of x dx. That gave a negative number, so I'm going to drop the negative there, so I'm going to put absolute value on this, plus the integral going the rest of the way, so from 2 to 6 of f of x dx. Based on the picture, we already know that this one's going to be positive, so we're in good shape there. So assuming I could come up with the actual measure for the antiderivative from 2 to 6, then I'll have my answer. All right. Now, if this were an actual function, you could pop it into the calculator complete with absolute value brackets and it'll give you the right answer. So that's good news. But, you know, we have a little bit of background work to do here, nothing too crazy, but it's still something that needs to be done. All right, so let me just kind of steal some room here. Oh. There we are. All right, so somehow I have to come up with the 2 to 6 interval. All right. So I know that going from 0 to 2, well, this marker isn't a little as crazy as the other one, plus 2 to 6 is the same as going all the way from 0 to 6. We already know going from 0 to 2 is negative 1.5. We don't know what going from 2 to 6 is. Now it's crappy again. But they told us what 0 to 6 is going to be. That's 3.5. All right. So that equation, which is completely property-based, is allowing us to figure out the part in part C that we need. Right? So by adding a 1.5 to both sides, I get that actual component. All right, so what that's telling me is that if I take the absolute value of my answer to part A, which would be 1.5, add to it what I just got, which is a 5, I'll get my result, which is 6.5. I mean, it's also something you could kind of reason out, because this is telling you, you know, you just kind of, I mean, I think it requires a little bit of talking to yourself, but you can get there by saying, all right, I have to end up with 3.5 when all is said and done. I'm going to lose some, I'm going to gain some along the way. If I know I'm losing 1.5, and I have to get to 3.5 as a positive number, what do I have to add to negative 1.5 to get to a 3.5 when all is said and done? I'd have to add 5. So that means that this guy up here has to be 5. So you don't have to set up an equation to do it, but knowing how to do it both ways is kind of nice. At a minimum, it's a luxury, but also at, you know, a deeper level of understanding all that good stuff.
So wouldn't be, the first part, where it is equal to 5, couldn't be 0 to 6 equal 5?
No, 0 to 6 we already know. That was the 3.5. If we're going from 0 to 2 to 2.2 to 6, then we're going to get 0 to 6 that way. It was this guy that we needed. All right. That one, by far, I think, is the trickiest one. And that's what I was talking about before, where I said it's a tricky question because it's a trick question. You know, that one's kind of designed for you to just get it wrong. Exactly. Not so much. I think it's the absolute value because it's loop. If it was a given function, you'd be all right. But really, I'll give you a visual on that one also, because I think it does tend to help. Let me just tuck it in over here. So this is C. So let's say you have some arbitrary graph, part of which goes below the axis, part of which goes above the axis. So there we go. Very arbitrary. So that's f of x. If I want the absolute value of that, Now, it's not the absolute value of the function itself, it's the absolute area. And that's what we need to keep in mind. What that's telling me to do is take any part that's negative, so this guy right here, for example, and come up with an equivalent positive area. All right, so take that and reflect it over the x-axis. Keep any part that's above the x-axis the way it is. All right, so when we're looking at f of x in the context of finding areas, then it is what it is. You integrate from left to right and call it a day. All right, and you could actually throw that information in there. So from a to b, f of x dx. It's when you want to work with absolutes. Graphically, this would be the equivalent. That's not to say that the absolute value of a function is just a reflection over the x-axis. That's not real. Right? Because if I have a linear function and I make it absolute, it plays out in that case. But what about like some weird transcendental function, like a log function? Not necessarily the case. But if you think about it, for the case of a line, right? Imagine the line y equals x. And when I say imagine, this works. Y equals x, zoom 6. Take the part of it that would give a negative area if you were to integrate, and redesign it so that it would only give you a positive area, equivalent positive area. In order to do that, you have to take this guy here and flip it over the x-axis. Right? So that's what our suspicion is. If you don't know anything about absolute value graphs, you'd say, okay, I'll take your word for it. But here's the absolute value of x, equivalent absolute value function. I'll bold it, make it more obvious. That's exactly what happened. Okay? So if I needed to find the area beneath or contained between a function and the x-axis, straight up integral, if I want to find only positive areas are talking about total area, I want to find the absolute value of that function and integrate that over. Okay. If it doesn't have an absolute value symbol, then it's just a straight integral problem.
But in that case, I think it would be 0.
Yeah, if it's symmetric, yeah. In this case, it would be 0. Any case in which it's symmetric on the interval would be 0.
So if I want to do the average from now on, set from negative whatever to 0 to whatever it is.
Yeah. Yeah, or you can do take 0 to whatever and double it to account for the total.
Not symmetrical, so it should be
Then you break it apart. Yeah, if it's not symmetrical, definitely. But the good thing about a non-symmetrical or asymmetrical graph is you can still find parts of it that are symmetrical. So I'll give you a quick example of that. I'm on an example roll. Crazy. So let's say you have, I'll do the absolute value function. Or I could do, I guess linear. I'll do linear, but not on a symmetrical interval. So something like this. All right, so this would be my A value, but I'll call it negative A just so it's a little bit more obvious. And then this would be my B value. All right. So if I need to find the area between negative A and B, I could do it this way. It could be a straight calculation. Or what I could do is find where negative b would be, which would just be the equivalent distance. Here's negative b. And I would know that these two guys would then cancel out.
So the answer would be a negative.
Exactly. We'd be looking at a negative area because the relevant interval would be completely submerged below the x-axis. But I'd be looking at an equivalent integral, or an integral that gives us interval that gives us an equivalent integral. So we'd be looking at something like that, right? So you can manipulate a little bit, but then it begs the question, like, what kind of problem are we working on that would require you to do something like this? If they give you a particular function, then you're just plugging it into the calculator anyway. It's when they give you some information about the graph, they say only find that piece. That's when you know that something like that is going to come into play, some kind of trick along those lines. Anyway, sorry. 0 to 2, negative 2 can be pulled out. It's only easy because we did parts A, B, and C already. We know that 0 to 2 is negative 1.5 multiplied by the coefficient, the constant multiple of negative 2, and you get a 3. Now the last one is talking about the average value. So we have the mean value theorem for derivatives and also for antiderivatives. I don't like the idea of having the same name really for two different things because I don't think I was really a victim of it, but it didn't feel too good when I saw it when I took the test. It was use the mean value theorem to determine this, right? And so I'm taking the test, and my first thought was, well, which mean value theorem is it? For derivatives or for antiderivatives? And so it depended on the context of the problem. So me personally, mean value theorem is always for derivatives. Average value theorem, which is basically the same thing with different words, is for antiderivatives, right? So when they ask you for the average value over an interval, they're saying to find the net area and divide it by the length of the interval. Or, formula, 1 over b minus a to b, f of x, dx. And the given interval is made up of the a and the b values. So I want the average value over 0 to 6 is 1 over 6 minus 0, going from 0 to 6, f of x dx. 0 to 6 was 3.5. So that ends up being what, 7/12? 7/2 times 1/6. So that's giving us a sense of the incremental accumulation of area. Okay? So we would have a net area overall. What this is giving us is the rate of change of area. It's telling us how fast the area is increasing per unit of distance along the x-axis. Right? So what this is telling us is that for every x value of increase, we're increasing in area by 7/12 of a unit. Right? So it's kind of a weird thing to get a handle on, but we generally don't want to. I mean, if I were to tell you that, we're talking gas mileage, and I would say something like you get 180 miles per every 7.5 gallons. You're like, okay, thanks, that's not useful information. But if I tell you you're getting 20 miles per single gallon, I know it's not equivalent, but 20 miles per gallon. Now you have a sense of what's going on. Every gallon of gas I use will give me 20 miles. Instead of thinking about it, it's like I got to use 7.5 gallons in order to use 180. Why can't you just divide the 180 by the 7.5 and tell me how much it would be per gallon? All right, that's the same idea here. This is telling us per 6 units, we would have 3.5, whatever the units of area are. But by finding the average value, it's telling us what it would be per single unit. Right? And there's a place for that in context. Right now, we're just learning the skill, or really reviewing the skill. Because in theory, this is all stuff you learned in Calc 1, right? That